I think the overshadowing idea for a first-year chemistry course is predictive power, being able to look at reactants, identify them by name or formula, predict whether or not they would react, and if they will react, predict what products would form. Be able to do that quantitatively with starting amounts and ending amounts and amounts that are left over. Do it for gases and aqueous solutions and masses, solids. And then do it in a laboratory setting. And like a big part of that is going to be stoichiometry. It ties things together real well. So we had lesson 1 where you got the idea of like, it's just a recipe and it's just ratios. And then we had the second idea where all of a sudden we had limiting reactants and excess reactants. The limiting reactant determines how much product can form. The excess reactant you have more than enough of and some's going to be left over. So the basic ideas we're going to look for here, like not even philosophically, but literally, how much product can we make from a reaction? How much did you actually make and collect in the lab? And what's left over? All right, I think those are 3 basic questions we can address. This is the process we're going to deal with every single time, and I'm going to try and squeeze it into this much space. So the first reaction we're going to look at, and again, looking at the big picture, here's some reactants, all right? Hydrogen gas and oxygen gas. We've got names, we've got formulas for those things. Will it happen? It does happen. We've got water. I don't care whether you put gas or liquid there, you balance it. All of a sudden we've made this a quantitative relationship between reactants and products, all right? So we have predicted that this product will form. Now, given some starting amounts, how much product could we make and how much stuff is going to be left over, right? And how much do we actually collect? So we'll need some information. We could do this in moles, like in the previous video, but we want to make it more practical, and mass is something we measure directly in lab. So I've made up some numbers to go with this. We'll just say like we're given 50 grams of oxygen gas and 10 grams of hydrogen gas. All right, so that's what we're starting with. And then we'll collect in lab 47 grams of water, all right? So that's a totally made up number, but in theory, that could be collected in a lab somewhere if this reaction was performed. So this is gonna get a little space intensive, and I'll try and budget well, but I don't have high hopes. All right, so the first thing we need to do, compare our reactants to each other, all right? And it's a 2 basic step process. Compare the reactants to each other so you can figure out which one is limiting and which one's excess, and then use the limiting reactant to find out about a theoretical yield. So I started those 2 steps. Everything else is icing on the cake for stoichiometry. So we're going to start with our 50 grams of oxygen and 10 grams of hydrogen. We need them to be in moles. You've done mass, moles, atoms type of calculations before. We're going to use the molar mass of that species from the periodic table. 2 oxygens is 32.00 grams per mole. And for hydrogen, 2 H's is 2.02 grams per mole. All right, so those green numbers I just wrote on the board are coming from the periodic table. 2 oxygens at 16, 2 hydrogens at 1.01. So this is going to get us a mole amount, and I will literally label this. Like, I think this is a key step as what you have, okay? That is the stuff we're given. This is how much we have of it in moles, okay? So I have these numbers written down. We've got 1.56 moles of oxygen, all right? And then for our hydrogen, we have 4.95 moles, all right? That's what we have. And I think it is very, very, very important that we have a logical way to set this up. When we were doing chemical reactions, we showed this reactant and product table so that anybody could look at it and say, okay, that's balanced. I know because the work is right here, not like, well, there's 2 times 2 is 4 and 4, and I already lost count. So the way we're going to set this up is going to be uniform for every single stoichiometry problem, and this is the way I want it set up, and it's going to be very, 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 very good in terms of bookkeeping. All right, I have 2 separate stoichiometry setups going right here, 2 separate dimensional analysis. I'm going to compare the reactants to each other. I've got oxygen, and for every 1 oxygen, right, 1 mole of oxygen, I've got 2 moles of hydrogen. I'm comparing the reactants to each other because I want to know which one I have too much of and which one I don't have enough of, all right? And this is something we practiced in a previous video. I was negligent here. This is 4.95 moles of hydrogen, all right? So as we're looking at this transition, 2 moles of hydrogen, everything after that first box comes from the balanced chemical equation. We've got 1 mole of oxygen. All right, this is what we have, and I want to turn it into what we need. All right, and I literally write the words have and need. It's good bookkeeping. All right, anybody can look at this and say, oh, this is the stuff I started with, and oh, this is how much I need, and this is why one is a limiting reactant and one is an excess reactant. So as we look at this, the 1.56, we double it, we end up with about 3.12 moles of hydrogen that we need, and we end up with about 2.48 moles of oxygen that we need. Okay, these are the numbers that matter. They're what I have. This is what we would need of the other thing to scale the amounts. Looking right here, I have 1.56 moles of the oxygen. I need 2.48 moles of the oxygen. I don't have enough. Anybody can look at that and see it. This is labeled very cleanly and very clearly. Very often stoichiometry is taught in this bizarro way where you're like, I'm going to take my 50 grams of oxygen and I'm going to turn that into moles of oxygen, and I'm going to turn that into moles of hydrogen, and I'm going to turn that into moles of water. I don't know. I never do it that way. I think that this is much cleaner, and it looks at the bigger picture better. If you set things up in a very organized way, down the road when you need to do like aqueous stoichiometry where you need concentrations of species in the final solution, there's no way you're going to do it with that rudimentary stoichiometry and keep track of anything. If you do it like this, anybody can look at it and see exactly what's going on. We're going to label it in an almost trivial way. All right, so have 1.5, need 2.4. I don't have enough. That is my limiting reactant that determines how much product we can make. Have 4.95, need 3.12. I have more than I need. That is our excess reactant. So we did that first step, compare reactant amounts to find the limiting and excess. As you look at it, we're going to find the amount excess by subtracting our haves and our needs, and I'll turn that into grams as well. And that's kind of an interesting number that we can use later to check if we've done things correctly. So to get our amount excess, I'm going to take what I have of the excess, right? There's no getting lost here. What do I have of the excess? 4.95. What do I need of that thing that is excess? 3.12. So we take the 4.95 minus the 3.12, and that's moles of hydrogen. And we end up with 1.83 moles of hydrogen excess. All right, that's moles. I don't think moles is necessarily super useful for in laboratory measurements. So we can turn that into grams. We just multiply by the molar mass. So the same way here, we divided by molar mass to get moles, we can multiply by molar mass, in this case, 2.02 grams per mole. And that's going to get us a mass here of 3.70 grams of hydrogen excess. All right, so there is our amount excess, if you want to like call it a number 2 right there and a number 1 right there. We have that. Now, overshadowing goal, we want to figure out how much stuff we can make, and we're going to do that, again, using this equation and a little bit of stoichiometry. We now know what our limiting reactant is, and that's what we can use to find out about our product. It determines how much product we can make. It's present in a stoichiometrically lesser amount, would be appropriate terminology. So I'm going to use that for my comparison, 1.56 moles of oxygen, right? And I'm going to use the balanced chemical equation, and this time I'm going to compare it to the products, all right? So for every 1 mole of oxygen from our balanced chemical equation, I've got 2 moles of water, all right? It's a 1-to-2 ratio, and moles of oxygen cancel. We end up in this case with about 3.12 moles of water, all right? That's a theoretical yield. Given 1.56 moles of oxygen and 4.95 moles of hydrogen, we can make 3.12 moles of water, theoretically. All right. And again, if we have a mole number, it's not inconvenient to turn that into a mass number. Same way we did down here. We'll multiply by molar mass. In this case, you could add up the pieces. 2 hydrogens is 2.02, 1 oxygen at 16. It's 18.02 grams per mole. And we end up with, in this case, 56.3 grams of water, right? This is our theoretical yield in moles and grams, right? our theoretical yield being the maximum possible amount of product given these starting amounts. All right? So how much product can be made? We've answered that question. How much was actually made? We were given that answer, and we're going to compare them in a minute. And what's left over? Well, there's 3.70 grams of hydrogen left over. Now, I'm going to mention this, although you can tune out if you're not feeling too comfortable with stoichiometry, but there's the law of conservation of mass. And in the end, in the beginning, we had 60 grams of stuff. In the end, we should have 60 grams of stuff. And it's a little unnerving if you say, well, we only ended up with 56.3 grams of water. True, but we also had 3.7 grams of hydrogen left over, and 56 and 3.7 ends up 60. So you can kind of keep track of your bookkeeping by looking for things like that. Started with 60 grams of stuff, ended up with 60 grams of stuff. That is what I made and what I had left over. So I think that's semi-useful, at least for keeping track and checking things along the way. All right, we want to get this information right here. Things are not budgeted space-wise very well on the board, but we'll give it a try. For this comparison, we're going to get a percent yield. That's supposed to be our actual yield over our theoretical yield times 100, right? And that's 100%, whatever that means. Our actual yield was given, okay? So one of the most common questions I get when we're doing these problems in class is like, well, where do I get that number from? It was given, okay? So you've got 47 grams of H2O, and our theoretical yield was 56.3 grams of H2O. We we divide and multiply by 100, and we end up, in this case, with 83.5% yield. All right? And that is how much we got compared to what we could have gotten. Once again, if you're wondering where this number came from, I made it up as like a representation of what someone might have collected in lab. And there's ways that percent yields can be higher or lower. All right. Just pointing at things very quickly. Get moles. Compare your reactants to each other to find limiting and excess. Use your limiting reactant compared to your products to find a theoretical yield. Along the way, you can get an amount excess, and you can turn your theoretical yield and your actual yield into a percent yield. And we'll try another one of these in a moment and see how that looks. All right, so we have a new reaction here. This is the Thermite reaction. You've got aluminum and iron oxide, giving you aluminum oxide and iron. You're reducing this rust to iron, and then you're turning aluminum into alumina, which is a ceramic. It's a white powder. So anyway, I've written some preliminary things. This number in orange here is 26.98. That's the molar mass of aluminum from the periodic table. Super common mistake is to think that this too applies to this number up here. No. This too comes into our stoichiometric ratios later. This number applies to just aluminum. This number applies to 1 iron and 1 oxygen added together. The 3 doesn't come into play. So 1 iron plus 1 oxygen, 71.85 grams per mole. Similarly, 2 aluminums, 3 oxygens, 101.96. And the iron on the periodic table, 55.85 grams per mole. This 3 doesn't come into play for that. It is used for our stoichiometric ratios later. I've made up some starting amounts here, 100 grams of aluminum and 300 grams of iron oxide. This is like the only chemistry joke I have, is that iron oxide is a super ugly compound. These are the things we're going to be looking for. How much stuff can we make? What is our amount that's going to be left over? And what is our percent yield? And to get a percent yield, we're going to have to be given some actual amount. If, we'll just say 222 grams of iron are collected. All right. So of note is the fact that I totally made this number up. It's a number that would be representative of some number that could be collected in lab. Like you do the reaction, you measure the amount of iron you get, and maybe it's 222. We'll see if I can do better with our space budgeting here. Remember our key steps. Compare the reactant amounts in moles to find a limiting and excess reactant, and then use the limiting reactant to find out about your product, or products in this case. And your theoretical yield applies to any products, and we'll see how that works. And then at some point we can figure out that amount excess. Okay? So we'll get going by turning this into moles so we can label what we have in moles. Aluminum, as we said from the periodic table, 26.98 grams per mole. Iron oxide, 71.85 grams per mole. And I did those calculations preliminary to get the numbers ready for you there. This ends up 3.71 moles of aluminum. And for the iron oxide, we've got 4.18 moles of ugly. All right. I will mention, like, I'm not going to be super cautious with sig figs on these calculations. If you've been in my classroom, that's contrary to reality. But for right now, I just want to keep things moving without ridiculous numbers. All right. Now, this is critical, right? Like, I have a very specific way I set these stoichiometry problems up. I'm looking down the road to how we're going to use these for solution stoichiometry and acid-base stoichiometry. And this is what I want to see. I want it laid out cleanly for other people to look at it and know what's going on. That's what we have. Those are our amounts that we have in moles. And we're going to be finding out what we need so we can find what we have too much of and what we don't have enough of. All right? Looking at our stoichiometry then here, we're going to use everything after the first box comes from the balanced chemical equation. This is 2 moles of aluminum for every 3 moles of iron oxide. All right? And for every 3 moles of iron oxide, we've got 2 moles of aluminum. All right? This will give us our numbers that we need to completely react with the amounts that we have. In the case of the iron oxide for the first one, it's 5.50 or 5.56 moles of iron oxide. All right. So 5.56 moles of iron oxide. All right, already screwed up my colors there. As you look at the aluminum that we need to use up our iron oxide, it ends up 2.78 moles of aluminum. All right. We can now make a determination if I have 3.71 moles of aluminum and I need 2.78 moles of aluminum, I have enough. In fact, I have more than I need, right? And again, we compare diagonally here because this is what I have and this is what I have of my other thing, and I would need this much of the aluminum to use up all that iron oxide. So let's make some notes here. Have 3, need 2, don't have enough. Or sorry, have too much. So that's our excess reactant, all right? Have 4.1, need 5.5, definitely don't have enough. That is our limiting reactant. Okay, so we did it. We identified our limiting and excess reactant. We did that so we can come up with a theoretical yield. I want to mention as a side note here, we had 300 grams of iron oxide, right? That's a bigger number than 100, isn't it? But the iron oxide was our limiting reactant, okay? And I'll say that again in slow-mo. We had more iron oxide by mass than the aluminum, but our iron oxide ended up the limiting reactant, all right? Don't assume that the bigger number here is going to be the excess reactant because we're looking at moles, not masses, and it all depends on the molar mass, all right? So this is a higher molar mass, and this wasn't proportionally higher in terms of the mass, so we didn't have enough of that, all right? And if those words didn't make any sense, don't worry about them, all right? We now know what our limiting reactant is. We now know what our excess reactant is. Let's sneak in a little work to show our amount excess. So for our amount excess, we have 3.71 moles of the aluminum, and we'll subtract the 2.78 moles of the aluminum, and that leaves us with 0.93 moles of our aluminum excess. All right? Moles are kind of an ambiguous concept for some people, but in a lab or on the street, somebody could look at a mass and know what that is. So it wouldn't hurt if we could do something meaningful, like say times 26.98 grams per mole, which is going to give us 25.1 grams of aluminum excess. All right. So either of those could be our amount excess. We'll call that B. I still don't have a theoretical yield, but I am going to have 2 theoretical yields, or 2 numbers, because I have 2 products. Our limiting reactant is what determines how much product we can make, so that's what I'm going to use down here for my theoretical yield. we're going to take our 4.18 moles of iron oxide, and we're going to compare it to our products using our stoichiometric ratios. So there's 3 moles of iron oxide, right? For every, and I will try and color code this in a meaningful way, for every 1 mole of Al2O3. So this is going to be one of my calculations, just so I don't have to write that twice. And that's 1.39 moles of aluminum oxide. So 1.39 moles of aluminum oxide. All right, that's my theoretical yield, how much aluminum oxide I could get theoretically if I used up all this with excess this. And so we can turn that into a mass amount multiplied by our 101.96. I don't really have a good color choice for that at this point. So we'll multiply by 101.96 grams per mole. And we end up getting for this 142 grams of aluminum oxide as a theoretical yield. All right. So that takes care of the aluminum oxide. We have another product though, so we're going to have another theoretical yield. We also have iron as a product. And let's see if I can use maybe blue for this. I know that for every 3 moles of iron oxide, there's 3 moles of iron. All right, and again, that's from the balanced chemical equation. So we've got 4.18 moles of iron oxide, 3:3 ratio, so that's 4.18 moles of iron that we would expect to see. We can do the same calculation to turn that into a mass. I multiply by the molar mass from the periodic table, 55.85 grams per mole. And we'll end up with a number here for the iron as 233 grams of iron. 233 grams of iron. All right. This then composes our theoretical yield for the aluminum oxide and our theoretical yield for the iron. If we were to add things up, we would expect to have about 400 grams of stuff, right? And what composes that stuff is whatever we made and whatever we didn't use up, all right? And I think as we look down the road, that's going to be a really important idea for solution stoichiometry. What you have in the end is whatever you made and whatever you have left over, all right? So, I mean, you add this up and you get 375 and 25 puts us right at 400, so that seems pretty reasonable. Again, in slow-mo, if you're interested, started with 100 plus 300, that's 400 grams of stuff. In the end, we had 375 grams of product and 25 grams of aluminum left over, which gets us that same 400 number, all right? So this work seems to check pretty well based on that information. The last thing we're going to get based on what we have here is that percent yield. So let's see what we can do. Percent yield is supposed to be the actual over the theoretical times 100. In this case, we're going to have to compare the iron actual yield to the iron, let me try it again, iron actual yield to the iron theoretical yield. The percent yield will be the same for all your products because they all came from the same place. But if I'm comparing how much iron I made to how much I could have made, it needs to be the iron, all right? So we'll look at our 222 grams of iron, right? We theoretically could have made 233 grams of iron, and we'll multiply by 100. And our answer here ends up squished along the bottom, 95.3% yield. All right. And that might be our answer to part C. Our theoretical yield here was our answer to part A, those things there. All right, something to note, and we'll look at this in a different example, is that if I know the percent yield of one product, I know the percent yield of the other product, all right? So I got 95.3% of 233 for the iron, and I have 95.3% of the 142 grams of the aluminum oxide that I actually collected in lab. This is already a mess, and I don't want to add that calculation here, so we'll do that in a later video.